right. So welcome. I'm happy that you came here for this talk. I'm Emanuele Sansone, and today I'm talking about self-supervised clustering and energy-based models. This is joint work with Robin Manave at KU Leuven in Belgium. So self-supervised learning has achieved impressive results in these days, and it has allowed the capability of neural networks to learn general purpose representations out of large amount of data. Once you have trained the neural network to learn these representations, what you can do is that you can tackle some downstream tasks. For instance, you can perform image segmentation, so you can discover the underlying objects inside an image, or you can also extract some properties out of the images, like for instance, performing depth estimation. On the other hand, we have generative models, which we are all familiar with, that can generate really compelling images. And here in this talk, we are going to look into the synergy between these two families of approaches. So we are interested in learning representations as well as synthesizing data. And probably one of the familiar models that people think about it when you think about learning representations and synthesized data is autoencoders like VAEs. And today we are going to see another family of models that satisfy these two complementary properties, which are the model that we are going to present is called JEDI. So this just highlight that there is a more general and richer family of models, and we are going to talk about this kind of wider spectrum. Now, there are different objectives. When I mean objective, I refer to functions that are used to train the neural networks. And so in self-supervised learning, we have different classes. Here are some of some of the main classes. I'm not introducing here uh, predictive models like masked autoencoders. This is out of the scope of this talk, but we are going to talk about these ones. So the correlation, contrastive, and clustering approaches. And on the other hand, for generative models, we can see the following classes. Now, what is interesting is that it is known that these kind of generative models are all, so what we are going to see actually is the connection between these objectives. We would like ideally to find a way to integrate these objectives into a unified perspective. And what is already known is that the current framework underlying these generative approaches is the likelihood formulation. So we formulate the training in terms of likelihood. Now, what we are going to show in our work is that we are identifying the common underlying principles behind self-supervised learning, and we are going to demonstrate that a similar principle holds for self-supervised learning, and so we can leverage the likelihood principle also for this family of approaches. Now, given the fact that we have identified that both self-supervised learning and generative models leverage the likelihood principle, we can go beyond that and highlight that there is an underlying principle called the entropy estimation, which actually enables you to integrate the two families. But we want also to go beyond that. And then what we will demonstrate is that we will select one of these, a pair of these examples of these approaches, like clustering methods and energy-based models. And we are going to show that we can unify them. So this is just to summarize the contributions of our work. We are going to see the formulation, an integration, and a unifying challenge. Now, just to be concrete, because this is kind of abstract, let's say, but the value of this theory is that we can come out with a unified model, as we were mentioning, so a loss that enables us to pick an untrained network. So we can think of this as an untrained classifier. And we are having some training data, some images that we are using. And then what we can do is that with this function, actually, we can train the neural network in an unsupervised way to perform several tasks. And we are going to see what tasks we can solve at test. So within a single model, within a single classifier, what we can do is that we can solve this task. So for instance, we can take our images in input, and then we can produce the underlying concepts. So we will make some predictions about what are the underlying concepts. So we will perform some clustering. Moreover, what we can do is that we can pick data that is not belonging to the training distribution. So for instance, here you can see a panda that was not observed during training. And so the model will be able to detect that this does not belong to the training distribution. So it will detect an anomaly. And also, thanks to the generative capabilities, we can generate data. So we can visualize what the network has learned. And moreover, we can use the concept to generate conditionally the data. So we can visualize conditionally what the network has learned. So these are all the promises of the talk of today. Now, I will dive into the details of the underlying theory. I will drive you through that. And so what we are going to see right now is the formulation. So how we can identify this likelihood principle for self-supervised system. And so let's start from contrastive learning. Let me give a brief introduction about contrastive learning. So in contrastive learning, we pick two images. Here you can see at the bottom. Then what we do is that we perform some underlying data augmentations, like we introduce some noise, we crop the images and so on. So we get two pairs of images, X1 and X2. We pass them through our neural network to get some representation. And then what we do is that we enforce that this representation for the pairs of images, X1 and X2, are similar to each other. Because the key idea here is that we would like to be invariant with respect to the transformation to the noise that we have introduced in the images. And so the underlying concept does not change in our data. And at the same time, since the two images at the very bottom are different from each other, we want to pull away the representations among these pairs. And so this is formulated using this criterion that people typically use to train a contrastive learning setting. Now, what we are going to show is that we are going to connect this criterion with the principle of likelihood that I was mentioning before. So let's look at that. In order to achieve this, what we identify is the corresponding graphical model, probabilistic graphical model that is behind this process, where essentially we have our pair of images modeled by this variable xi. So n here n refers to the number of training samples that we have. So these are our pairs of images. And then we have an indicator variable that that assume a value between 1 and n. So we have all the indicates which kind of pair we are referring to. And so given this probabilistic graphical model, we can define the underlying ground truth, which consists of an unknown density here. And then we have the conditional of y given xi, which is just an indicator. Okay, so it identifies the kind of pair you are considering. And so then you can define the underlying ground density. Now we can provide the definition of the approximate model. Again, for us, the underlying distribution for xi is the same as the ground truth. And then we identify an underlying classifier. Here you can see that this is a classifier, can be thought of as classifier. So now what we can do is that we can express this softmax in the expand this softmax, and we see that these two quantities are the same, so we can replace this kind of thing here. And then we can highlight that this objective is actually a lower bound on the entropy, on the negative entropy of the ground truth model. Okay, so that's how you are actually highlighting the likelihood criteria. And so from here, I'm not going into the details of that, but you can check out the paper. You can derive the other objectives that are commonly used in contrastive learning. Now let's look at the correlation methods. So in the correlation methods, we do a similar um, processing of our data. So we pick our image, we perform some data augmentation, we pass through our encoder, our neural network to get some encodings here. And then what we do is that we try to force that these two encodings, similarly to before, are similar to each other. So if we maximize this quantity, essentially we force these encodings to be similar to each other. And so we want to be invariant with respect to the underlying data augmentation. Now what we can do after that is that we have an additional network here, a projector, that actually translates these encodings into embeddings. And now from these embeddings, what we do is that we compute across covariance matrix. So we collect the embeddings over a full training data set, then we compute this cross covariance matrix. And then what we do is that we force this cross covariance matrix to be close to a diagonal matrix. And so in essence, what we are doing with this second loss function is that we are forcing the elements in our embeddings to be decorrelated from each other. So the loss typically used in contrastive decorrelation approaches is based on these two criteria. So now let's look at the underlying probabilistic graphical model behind this objective. And so we see here the image, the underlying transformed image, and then we have two latent variables. The first latent variable, Z, actually captures the global information of our dataset, whereas Xi here actually refers to a specific instantiation of our example. So it's a specific instance of our training dataset. Now we can specify again our ground truth model where we have the underlying unknown distribution here. We have the conditional of xy given xi, which is just the data augmentation strategy. And we have the prior over the latent variables, which are just simply standard governance. Now let's look at the posterior model. So here what we do is that we just define the one-to distribution to infer the values for the latent variables. And so we see here that the posterior for Z, given all our images, is defined by a Gaussian, which has mean 0. And then we have a covariance matrix that is defined in this way, which is just the support covariance. Okay? And then we define also the posterior for the latent variable xi, which has some mean value and an identity covariance. So the mean value in this case is just the difference between the encodings of our images. Okay, now what we can show is that if we look at the prior here and the posterior, we see that the two densities are two Gaussians, and the only difference between these two things is the mean value. So here we see that we have a mean value that is given by the difference between the two encodings, and these two encodings, somehow this difference should be close to 0 as possible. And so we can express this distance in terms of KL. Now, if we look at the other loss function, we see that the two distribution here share the same family, and the only thing that changes is the covariance matrix. And so by forcing this distribution to be close to 1, to be close to the prior, we force the sample covariance here to be close to the identity. And so we can express this quantity in terms of the Kullback-Leibler divergence. Now that we have identified we have rewritten these two losses in this way, we can highlight that these two losses actually are still a lower bound on the negative entropy of the ground truth model. And so from here, we can derive other kind of families of approaches for the correlation methods. And now I think you got a sense of how you can derive things. We are going to quickly check the clustering approaches, but in essence, the story is the same. So in clustering approaches, what we do is that we pick our image, we perform data augmentation as before, and then we have two networks, so which share only one part. The only difference between these two networks in the upper part here on the right side, let's say, which involves clustering algorithm. So in clustering approaches, we use a clustering layer here to partition what we have in input, let's say, to get some cluster assignments that can be used for training the neural network. And this is typically introduced to avoid learning trivial solutions, let's say. So it introduces an asymmetry to avoid the neural network to collapse to some trivial solution. And the loss that people typically use is similar, is defined in this way. You have a distance that forces the two representations here to be close to each other. So somehow you enforce some sort of variance, as we were mentioning before. And then you want also that you want to somehow maximize the entropy of your clusters. So you would like possibly to leverage as many clusters as you can. Now from here, what we can highlight again from the loss function, we can identify what's the underlying graphical model. We see here the image, the augmented version, and then we have a categorical variable that actually goes from 1 to the number of clusters. So again, we can define the underlying ground truth model with the underlying unknown density, the data augmentation, the stochastic augmentation. Then we have our classifier and the joint. From here, we can define the posterior, which actually, as I was mentioning, it uses part of the neural network that we were seeing before. And then we have a sort of clustering layer that actually performs the underlying clustering. So now that we have specified the whole model, we can highlight again that this objective is essentially a lower bound on the net entropy of the ground truth model. Right. So we have shown that clustering self-supervised learning approaches all share a likelihood principle. And now what we are going to do is that we are going to highlight the fact that the underlying classes here, the two classes actually can be integrated into a common principle, which is the entropy. So these are the three lower bounds that we have seen before. We can see that these three lower bounds actually have a common term here that has not been exploited so far. So if we work out the underlying term here, this is defined in the following way. So which is essentially a negative entropy of the underlying unknown distribution. If we introduce a generative model, we can p theta, we obtain a lower bound on this quantity. And this is essentially a entropy term, a likelihood term. Now, if we replace the top, actually we obtain our overall objective function, where we have now a likelihood term here for a generative model and a likelihood term here for computing performing self-supervised learning. Now, this kind of framework actually encompasses previous solutions that people have proposed in the literature. So you can see, for instance, contrastive learning approaches using VAE as a generative model, contrastive approaches using an EBM, and clustering approaches using UniBL. So these are all ways to integrate self-supervised learning approaches with generative models. Now that we have seen the integration principle, let's move to the last part, which is the unification, and how here, and now here, what I will give the secrets to achieve this kind of unification. So I will guide you step by step towards achieving this unification. So now let's recall the clustering framework. So this is the lower bound that we are mentioning before. Above, we have a classifier and the other branch, that the other network that uses the clustering layer. So we mentioned that we want a single model. And so the first thing that we do is that we just use a single classifier. And now if we do that, let's say, and we try to, if you try to learn, let's say, this classifier using this loss function, you will figure out that there are some trivial solutions. And one of these trivial solutions is the following one. So if you take a classifier that predicts always a uniform distribution, essentially you get a local optimum on these for these objective functions, and you cannot escape from that. And so the question is that how can we avoid these trivial solutions? Well, the first thing that we can do is that we can modify our objective function. So for instance, what we can do is that we can modify this and use a cross entropy objective that forces these two distributions to be close to each other, where these distributions are a uniform prior over y. And then qy here is just the marginal over, essentially we average our classifier over all the output of the classifier over all our. We are going to see later why this avoids the trivial solutions. Now, the other step that we want to do is that we want the generative part. So far, we haven't exploited it. And so what we can do is that we can leverage the previous trick that I was mentioning, and so we can replace it with a likelihood for the generation. But now we have to specify what this generative model is. And so what we can do actually is that we can express our classifier here, expanding the softmax, and noting that this conditional density is just a ratio of a joint with respect to a marginal. So from here, we can see that we define the joint and the marginal in the following way by introducing a constant here, and we replace it back to the ratio, we get back our softmax. And so this gives a way to extract a generative model out of our classifier. Now, this was the secret sauce. So we have our objective function, and then we have our classifier and the corresponding generative model. Now, what we want to show is that these three terms in the objectives are necessary or sufficient to avoid this kind of issues. And so let's look at what are these problems. So representation collapse is the problem where your neural network, essentially when you give in input to these kind of images, predicts always the same concept. Another issue is the cluster collapse problem, where essentially some of the concepts overlap each other. And so for instance, here you cannot distinguish between these two concepts. And finally, you can be inconsistent with respect to your data augmentation. So for instance, if you perform some transformation of your data, you add some noise, it can happen that your neural network actually switches the output. So it is undecided. Now, what it turns out is that each of these kind of objectives actually is able to avoid one of these problems, only one of these issues. And so it is really essential that we use all three of them. All right, so this concludes the part of the derivation and the theory and so on. And now let's look at the experiments, and I will try to give you an intuition about the different objectives. So here we conducted an ablation study just to highlight the underlying properties of the three different objectives. So, and what you can see here on the left is that we have two data sets in two dimensions. And so each of these dots you can think of an image, and the corresponding color corresponds to the value of the concept. So we have two concepts here, the blue concepts and the yellow concept. Now, if we use only the generative model, okay, so only the generative loss, what happens is that we end up to predict only one concept. So we have the cluster collapse problem. Again, if you use the generative model plus this kind of invariance loss, we face again this problem as predicted by the theory. If we instead use the last term, actually we start to get rid of the issue of collapse, of cluster collapse. But you can see that the underlying predictions are non-smooth. So there is the problem of being inconsistent with the transformation in our data. If you use only the self-supervised loss here, you have almost perfect prediction. So you see that for the first data set, you perfectly cluster the data, but once you have some particular symmetries, you have difficulty to cluster that. And then once we use all the three losses, we avoid these kind of issues, let's say. So we can show some animation of a generative approach, a clustering approach, and ours with respect to clustering and generations. And so here is what you can see the qualitatively what's going on. So you see that after this is training, so after training, essentially only our model can enable you to perform clustering as well, generate the underlying data, visualize what is the distribution that the model has learned. Now let's look at the experiment on real data. So what we did here is that we consider three data sets. We have street view house numbers and then some naturalistic images. We compare our model with respect to a generative approach and a clustering approach. And what we can see is that the clustering performance somehow of our model and the baselines are somehow comparable. In some cases, we are better than that. But what is really important is to see that the generative model, which is not designed to perform clustering, really is not able to predict the underlying concepts in our images. And moreover, what is interesting is that when we evaluate the generative performance, we can perform comparably to the generative model, whereas the clustering approach completely fails at that. And in order to gain some insight about this gap, let's look at some animation on the generation. So this is what you observe from a clustering approach here on the left, when you try to generate data out of your classifier. And this is what you can get out of our model. Another task that we can solve or tackle is the out-of-distribution detection. And so here what we do is that we train our neural network on a data set of numbers, and then what we test what we do is that we test on a different data set whether the data belong to can be detected as out of distribution. And so what we can see here actually is that if the performance are above this kind of black line, somehow the models is capable of predicting correctly the out of distribution, that the data is out of distribution, whereas if it is below the bar here, the model predicts in distribution, that the data is in distribution. And so we can see that the clustering approach actually confuses the examples as in distribution. So it's not robust to out of the distribution detection. I don't want to confuse, I don't want to give the wrong message here that we are solving out of distribution detection. And there are cases in which all models have difficulty to do the tasks. And so this is one example. You can see that if you train on CFAR10 and you test your model on S-mail chain or CFAR100, the model has difficulty to determine whether it is out of distribution or in distribution. So this is a known problem that is actually reported in the literature, and I recommend to, if you are interested, to look into this paper. One thing that I want to highlight about this, the application of this approach is related to the symbol grounding problem, which was introduced in 1990 by Harnack in the and is a known problem in AI, in artificial intelligence, and was later popularized by Barceló in psychology and cognitive science. So what is this problem? Imagine we have some data and then we have some knowledge. So the symbol grounding problem actually consists of being able to ground the symbols here in the data that you see. And so in order to in order to evaluate the capability of neural network or a perceptual model, let's say that is processing the data, we want to be able to learn a mapping from the images to the symbols that actually satisfy the underlying knowledge that is coherent with the underlying knowledge, but also capture the underlying concept in our images. And so the symbols should be grounded in the concepts of the images. And so what is interesting here is that the neural network predicts a distribution over the possible digits, and that this distribution actually is combined with this kind of program to predict whether the knowledge is satisfied or not. And so this is how we are going to define the underlying program here. So we have a bunch of probabilistic facts over the possible digits. Then we have a rule that actually takes these 3 digits and constrain them with respect to the rule that I was mentioning to determine whether the output is true. Now, what we do is that we can give a bunch of these samples in input, and we can train the neural network to always predict. So if you do that, actually, it turns out that the neural network learns a wrong mapping where essentially it puts all the mass to the digit 0. And so that actually is a solution to the underlying rule, but it's not a desired solution because it doesn't capture the underlying information in our data. And so we discuss completely the information in the data. And so now that we are mentioning about the representation collapse, we can think of using JD, the method that I was proposing before, to tackle this issue. And so here what you can see is that we perform some analysis of the performance in predicting the digits. And so we compare the neurosymbolic approach, which uses the neural network and the underlying program. So it trains the neural network to be compatible with the underlying program. We train also the neurosymbolic approach with a clustering baseline, and then the neurosymbolic approach with our new loss function. And so here, what you can see is that all the baselines actually face this kind of issue, whereas our approach actually is able to overcome the problem. And so notice that the performance is on the x-axis here. You see the number of training samples that you have used to perform the test. And so even for 1,000 examples, we can almost solve completely the kind of issue. What is actually interesting is that even for a small amount of examples, like 100, we perform significantly over the kind of collapse that the other approaches observe, face. However, there is still a huge gap that has to be uh, uh, reduced. So another interesting aspect is that when we compare the clustering performance, we see that the clustering approach improves over the number of examples, but it doesn't achieve the similar performance of our approach. So to summarize, what we have seen today is that we have proposed a likelihood formulation for several self-supervised learning approaches. We have highlighted that we can integrate self-supervised learning and generative models using the principle of entropy estimation. And we have proposed a new family of models that unify self-supervised clustering and energy-based models. Thank you. Any questions?
So you mentioned that with the Jedi framework, you can both generate and classify. So how do you basically how do you do that? Like, there are two modes to the network, like with generative mode and classifying modes. How does that work?
Yeah. Let me go here. Um, so for clustering, let's say for predicting what are the underlying concepts, let's say you just use the classifier. So it's just a forward propagation of your input. And for the generative model, actually, what you do is that it's a sampling strategy, okay, which is a gradient-based strategy where you essentially initialize X, your image, with a random noise, and then you perform some gradient steps, let's say, that push you towards regions of high density. So that's the way in which you do that. When you compute the gradient, you also add some noise. It's a MCMC strategy that people use to sample from an energy-based model.
Go over how you avoid cluster collapse again.
Sorry,
Can you go over how you avoid cluster collapse?
which one?
This cluster.
This one?
Yeah.
Why it avoids cluster collapse? Yeah. Let me. Okay, here. So what we do here, okay, is that we are um, averaging over all training data, the output of our classifier, right? And we want this average to be close to a uniform prior, right? This one, right? So what essentially this loss is doing is that it's saying, okay, I have all my data, and all my data gets assigned to some of these clusters, right? But on average, I want to use all of them, and that avoids the cluster collapse.
Thank you.
Instead, maybe just to have an additional clarification, instead, this kind of loss is pointwise. So you're forced to have high entropy, but within a single example. And so that can just introduce some noise, let's say, in your prediction.